Yes.
And the topic of Nicolas' talk will be quantum normalization of 2D Bose superfluids. Very much looking forward to your talk.
Yes. Can you hear me? Yes. Okay. Okay, so good morning. Good morning, everyone. So I would like, first of all, to join with the previous speaker and thank the organizers for inviting me today, and also for setting up this very inspiring conference on collective phenomena. So the general topic of my presentation is the non-equilibrium physics of many-body isolated systems. And to illustrate this topic, which we have heard about a little bit in the previous days, I would like to start with a pretty simple classical example. Okay, so suppose that you initially prepare here two classical gases, so two Boltzmann gases in two compartments here, separated by the wall. And here I also suppose that the whole mixture is completely isolated from its environment. The two gases here are two different total energies, different temperatures, if you wish. And now suppose that, say, at T=0, you suddenly remove the wall between the two compartments. So then, obviously, the two gases start to mix, so that the system is clearly out of equilibrium. But if you look a little bit more closely at this microscopic dynamics, you see that very quickly the dynamics becomes more and more stationary, more and more continuous. So this phenomenon can be directly traced in the individual energies of the two species here, ER and ED, which evolve in time because you have, of course, particle conditions during the process, until the system reaches here a stationary state characterized in that case by equipartition. So this initial process that puts the gas out of equilibrium is what we call generally a quench here, because it's a fast process. And the mechanism by which the system relaxes at long time to what is here a thermal state is what we call thermalization. Right, so this is a classical example. Now let's move to quantum systems. So in quantum systems, this is the typical question that you have. So you initially start from some state, which may be an eigen state of your Hamiltonian. Then you quench it, and you change roughly a parameter lambda this Hamiltonian, say from lambda alpha to lambda f. And then you just look how the system evolves unitarily under the change. And then, very much like in the classical example, the natural question is, how is thermal equilibrium reached at one time? And maybe also interesting, and perhaps sometimes more interesting, can't the roots to the thermal state also reveal interesting out of equilibrium phenomena, universal, possibly universal phenomena? And so now that we mentioned, just as a remark, that of course in a strict sense, here thermalization should not be understood in terms of the property of the whole system, because the whole system can actually not thermalize in the sense of density matrix converging to a thermal one, just because the evolution is unitary. And in particular, you see this immediately with this example. If you start from a pure state, if you have a unitary evolution, then the purity is one at all times. So it cannot be a thermal state. So rather, thermalization is understood in terms of local observables, so observables which are defined in a subpart of the system. And for these observables, generically, the expectation value at times converges to an average over an effective Gibbs ensemble. This is what is called the eigenstate thermalization hypothesis. Right. So now it turns out that in previous years, one focus of statistical physics has been precisely on the deviations from thermalization in many-body systems. And we have seen already a couple of examples 2 days ago, but here I listed a few of them. So the main one is integrability, which typically challenges thermalization, at least in a conventional sense.
No. Okay. So can you go to Zoom?
Okay, so integrability can hamper thermalization, like in the Liebig-Bose gas in 1D, but you have also other mechanisms, for instance, disorder, which is a known ingredient to hamper thermalization by a phenomenon called many-body localization. And we have also heard about many-body stars here, which are exceptional eigenstates in certain systems, whose property can deviate from the hypothesis of ETH. And so they can also question the thermalization process. So in this talk, the Bose gases, the weakly interacting Bose gases that I will discuss actually belong to yet another category of systems which are near integrable ones. So in a weakly interacting Bose gas, if you wish, because interactions are weak, you are close to the non-interacting unit, which is by construction integrable. And in near-integrable systems, an interesting phenomenon happens, namely thermalization takes place, but usually it is repelled to long times, to very long times. And specifically, you have a separation of timescales. We have shown down here the fast emergence of what is called a pre-thermalization regime or pre-thermalization plateau, where your correlation typically changes, but very slowly in time. And only on a much long time scale does the system relax to thermalization. So this kind of dynamical scenario has been explored in many systems, both numerically actually and experimentally as well. So here you have a numerical example in the Fermi-Hartree model. I think they looked at something like the occupation number at the family level after a quench, and you see that for small interaction strength, you have this emergence of this pre-thermalization plateau before the conventional relaxation. So this is an experimental example from Schmidtmeyer's group in Vienna, who did one of the seminal observation of pre-thermalization about 12 years ago. So what they did at the time is they took the VC, they split it into two parts, and then a long time after the splitting, they recombined them to observe interference. And what they found is a very robust persistence of coherence over long times, suggesting a very slow thermalization process actually of the two parts of the VC. All right, so now let me go into a little more details. So usually, fundamental property somehow of the pre-thermalization regime is that, in general, at least for weakly interacting gases, it can be captured by a picture in terms of independent quasi-particles. And this explains why, in fact, the system in this stage behaves a little bit as if it was integrable. That's why it does not thermalize here. In contrast, so yes, so because you have quasi-particles, the dynamics is also coherent here, and it involves a certain fast scale, which is essentially the inverse of the quasi-particle energy. Now, in contrast, the thermalization process involves interactions between the quasi-particles, which involve certain relaxation processes, which of course depend on the system under consideration with a rate down. Right, so now I come to the context, the specific problems studied in the talk. So what we investigated recently are quantum quenches in 2D Bose gases. So here I show you the equilibrium phase diagrams of 2D Bose gases, just as a reminder. So in 2D Bose gases at equilibrium, you know that you have a thermodynamic phase transition, which is the post-realistic transition. Above you have a normal phase, natural gas, below you have a stationary gas, which has also supercritical properties. And this is equilibrium. And in this basic equilibrium framework, the simplest quench protocol that you can consider is this one. So maybe you prepare your bose gas very deep in a supercritical phase at some very low temperature TR. And then you quench it, and here you quench it gently enough so that it re-thermalizes in this phase at a long time. Of course, you could imagine a more complicated scenario, but this is the one I will discuss here. And I show you that it can be pretty rich and it recently falls in the two-step process. All right, so this is the plan for the rest of the talk. So I will first show you how to describe theoretically this pre-thermalization to thermalization crossover using a quantum theory in our case. And then I will apply this theory to a pretty simple observable, which is the coherence function of the bose gas after typically an interaction approach. And then I show you experimental illustration of the results in the end of the first part. Then in the second part, I will look at something a little bit more tricky, which is a very long time behavior of the bose gas after a quench. And I show you that when the system approaches the cell state, the dynamics can be quite non-trivial and in particular unusually slow, exhibiting algebraic phase. Okay. So let me begin with simple considerations onto the bose gases. So the starting point is the minimally Hamiltonian for bose gas with recursive contact interactions. So in low dimensions, it is convenient to use what is called the density field representation of the field operator, using that since we are constantly low temperature, the density fluctuations are slow. So I can expand with respect to these fluctuations. And by doing so, I end up with the hydrodynamic form of the Hamiltonian. So you have here quadratic part and cubic terms. So this form is not too convenient because the quadratic part is not diagonal. So the usual trick to solve this is to use the local transformation. So you introduce more operators, A and dagger, which are linear combinations of less complex fluctuations. And by doing so, you end up with the Hamiltonian law quasi-particle basis. Of course, the Bogoliubov transformation does nothing to the cubic terms. They are free there. But a good point is that the quadratic part not takes the form of a chain of certain harmonic oscillators, and these oscillators are the quasi-particles of the system, the Bogoliubov quasi-particles, which have this dispersion. The dispersion is linear homology, which is responsible for the superfluid properties. And then you have the cubic terms, which actually describe interactions between quasi-particles. So now let's do the roughest approximation and simply discard these cubic terms. So if you do so, the dynamics in this basis is trivial, with the Bogoliubov operators just oscillating forever in time. And coherently, this is exactly the same nature of the system lying on the pre-thermalization regime. The pre-thermal regime, the dynamics is fully coherent, is controlled by a time scale here, which is essentially the inverse. A simple consequence of this approximation is that the momentum distribution of the phonons, quasi-particles and phonons have no energy, more specifically the normal and the anomalous distribution, which is also important for the dynamics. Lots of them are actually time independent, except for this oscillating factor. So this means that essentially they match their initial value. And this is another property of the pre-thermal regime. In the pre-thermal regime, the system retains minimum from its initial condition, unlike the post-thermal state at very long time. Good. So this is for the pre-thermal regime. So now to describe the crossover to the thermal state, we need to include these interactions. This is the difficult part. Here I won't enter the details, but for long part we have resulted to non-equilibrium quantum field theory which is a very convenient approach because it's well adapted to perturbation, expansion, and time-dependent problems. So here I will just give you the outcome of this approach, which is pretty simple. It consists of quantum kinetic equations for the momentum distribution. And in particular, if you look here at the kinetic equation for the normal density, it takes a pretty simple form. It's actually simple, but it's still simple. And you have a collision integral here, which essentially describes the competition between two quasi-particle processes, which are called London scattering processes. So they essentially consist of the recombination of two formulas into one and one superconductor. Right, so what you need to do in general is to solve numerically these equations for given equation to go, but they also have generic properties, and in particular, this one, the generic property is the stationary solution, which is nothing but the thermal distribution for the quasi-particle. So in other words, with this approach, on paper, we can describe all the many-body dynamics from initial quench to the long-time thermalization. Notice here there is a temperature, which is the temperature spontaneously acquired by the gas at long time, and this one is this temperature is controlled by initial condition together with the conservation of total energy here, which is an integral motion. Right, so now let me show you one example, one application of this theory. So here I consider a very basic problem. I start from a 2D superfluid initially at equilibrium at some temperature, Ti, and I consider that at T equals 0, the interaction strength is suddenly changed from Gi to Gi. So this induces a non-equilibrium evolution, and to characterize this evolution, we have looked at several observables, but in particular at the coherence function of the both gas as a function of time after the quench. So this expression is shown here. Notice that it depends on this quasi-particle distributions. If we compute them, we can have a G. So this is how G1 looks like. So the dash curve is initial time. At initial time, you just have a quasi-common state at equilibrium. So the coherence is algebraic. And the exponent here of the quasi-long range order is controlled by the thermal double wavelength at the initial temperature. Then you quench it, and when you quench, you see this the G1 function evolves in time within a light cone, which essentially tells you that the correlations cannot spread faster than a certain speed, which is the speed of sound. And what's interesting for us here is that within the light cone, if you look a little bit, you see that the G1 function actually is quasi-stationary. And in addition, in the light cone, it also decays algebraically, but with a different exponent. And this is again a signature of a pre-thermal regime. Pre-thermal regime, the system is non-stationary, the correlation is non-stationary, and the system looks as if it was at equilibrium, but at last, because the exponent here is not the one we expect. But of course, as time goes on, and quasi-particle interactions come into play, they modify a little bit the shape, and if you look here at long time, you see the emergence of a new region of algebraic coherence at the core of distribution elements becomes larger and larger as increases. And now, if you here look here at the algebraic exponent, it corresponds to the temperature you expect for the thermostat at the moment. So you have a picture here where we can describe the fluid dynamics up to the thermostat. Now, this protocol has been actually realized experimentally. So this is an experiment that was done by the quantum optics group at NLA, by my colleague Quantum Review. So this is not an experiment that involves gold atoms, actually, but here it's non-equilibrium photons. So the setup here is pretty simple. You have a laser illuminating nonlinear material, nonlinear paper. And the point is that in this paper, the estimate of the electric field is governed by the nonlinear optical paraxial equation, which is completely similar to Bose-Potayevsky, with here an interaction wedge at the interface between free space and the material. And so, if you look at the propagation of matter reproduces the dynamical, the midfield dynamics of BC, the two-dimensional Bose gas, out of equilibrium. So, following this analogy, what we propose in 2020 is to inject in this material a laser which is as flat as possible in the middle with shallow spectral fluctuations from the top. And the idea is to mimic the thermal fluctuations that you would have in a true quantum gas. And so by doing they could do this, and then by measuring here the interference between the transmitted beam patterns to two arms, they could directly compute or measure the coherence function, and they observe a very nice emergence of algebraic coherence from the light cone with here the Stevenson. There was also the year after a very similar experiment involving co-atoms in the group of Chris Foot in Oxford, but here they also did actually a bit more particular question across PPT transition. Right, so this is now the second part, and in the second part, which will be much shorter, I would like to make one step forward and not only discuss the crossover from pre-thermalization to thermalization, but also the limit of very long times, where the system approaches the equilibrium. So now it turns out that in kinetic theories, the conventional view is when you have a Bose gas to perturbate, it will generally reacts exponentially to equilibrium. That's conventional view, and the time scale is typically the phonon scattering rate, which can be computed by many ways, for example, with chemical rule, as was done by Nicolas in the 90s. So this is the conventional view. In fact, it's not at all exponential, not at all obvious that this relaxation should be exponential in most situations, in particular when starting from far from equilibrium. So recently we decided to investigate a little bit more this problem, and by considering, in fact, on purpose, a situation where the initial phonon distribution after the quench is very far from the thermal one expected at long times. And in a nutshell, what we typically designed the quench protocol in such a way that the phonon distribution immediately after the quench scales as 1 over q squared at low energy. And the point is that this 1 over q squared is extremely different from the 1 over q that you expect at low energy. And then we run the kinetic equations. So here you see the phonon density momentum distribution at different times. And if you look at the red curve, which is the longest time scale in the bridge, you see that actually the thermalization process involves 3 dynamical regions in momentum space. So if you so they are separated by these two momenta, QE and QT. So if you are below QE, you see that the relaxation has not yet started. This is by definition the thermal regime that is at the outset. Then the relaxation is effective. You start to approach the thermal curve, and after some momentum here, it seems that the system has relaxed. This momentum has relaxed. So let me focus now a little bit on this region. Let us look first at this intermediate region. So this is just the same curve of rescaled. So here I plot the deviation of the phonon density to equilibrium versus gamma t, the rescaled momentum, in log scale, and in this way we can directly check whether here the relaxation is exponential or not, and clearly it's not. This would be the exponential prediction. Rather, we have identified numerically and also analytically what we call the anomalous Landau relaxation, where you have actually a dominant exponential factor, but the relaxation rate is not given by the thermal rule. And you have also sizable algebraic corrections. Then we look also at the region here where currently the modes are relaxed. And in fact, we found that it's not quite the case. Again, by rescaling, we have found that in this region, in fact, even if the modes are very close to equilibrium, the residual dynamics and this residual is purely algebraic. Actually, it reminds us a little bit of the diffusing process. So it means that even when the system is extremely close to equilibrium, there are still modes that relax extremely slowly, according possibly to what we think is a diffusing process. Okay, and in particular, the exponential relaxation never happens. Okay, so from this analysis, we could construct a full dynamical portrait of thermalization for our 2D superfluid. So this tells you essentially for a given quasi-particle momentum, what is the status of relaxation. So at short time, it's with thermal. Then you have this anomalous Landau scattering, and eventually when the system, let's say this momentum is very close to equilibrium, you end up with an algebraic relaxation. Just a quick word about this algebraic relaxation. Actually, if you apply energy conservation at a given time, and if you segment here this condition over the three dynamical region, you can actually relate here the photon density at large momenta to the contribution of energy from low momenta. And in short, if you use in addition that the scattering rate of photons is linearly Q, you can estimate this left-hand side, and you find that it goes like 1 v. So in other words, it seems that here the algebraic relaxation at long time is determined by energy conservation and also by the mechanism of quasi-particle scattering. And what's interesting is that if you extrapolate these arguments, in one it turns out that the scattering rates are differently with Q. And in that case, we find that the photon distribution at long time goes like T to the minus 2/3. And in this paper, this was associated with KPC. Would suggest that we have here one D gases KPC dynamics at long time. So that's the end. I wanted to show you that we can, with some approximation, describe reasonably well the full many-body dynamics of dilute superfluids. The pre-thermal stage in particular could be experimentally, it's much difficult for long times. We have also many other open questions in the group, in particular, what happens for quenches across the phase transition, which is much more difficult to trade theoretically, or also for non-equilibrium physics in both mixtures. I would like to acknowledge my group in Paris at the Sorbonne University. And in particular, Clément Duval, who's what I presented today, is his PhD work, and I would like also to mention that most of the positions students are interested in. Thank you very much.
Very much for this nice presentation, and sorry for question.
What can you say about the time scale or the duration of the pre-thermal plateau of these fields? Like, is there anything universal about it? Is it supposed to be parallel, exponential, etc.?
No, you mean the time scale where the pre-thermalization plateau arises?
Where it ends.
Okay. Well, it's difficult to say. Okay, in the beginning, I presented in my sketch like a sharp, rather sharp transition. In fact, it's a very slow crossover. So the time scale is just yes, it's the scattering rate of the quasi-particles. So this is not universal. It depends a bit on your system. But so if you take the recent cold atom experiments, for example, almost all cold atom experiments doing this kind of quench physics, usually they don't reach. It's difficult to reach the thermalization regime, but usually with cold atoms, typically you start to see this relaxation after a few tens of microseconds. They can observe, they see the relaxation of quasi-particles within the rich experiments. And if you take, for example, in the optics experiment I presented, it's completely different. For example, because there is no time, actually, the effective time is the length of the medium, and they have a length of a medium which is centimeter, and we are currently investigating whether they can see this crossover. Probably it's after a few centimeters, and that is, they are very strong non-linearity. So it's not universal. Yes, yes. So that so when you question, okay, the difficulty. So the reason why we can solve the problem here is that we have just one kind of percentage So when you question cross the transition, now you have the vortices. So you need to describe the dynamics of fluids and vortices, especially vortices. So this model is not well adapted. You need to use other models that include vortices inside of the fluids and things like that. So this was studied in the group of Chris I mentioned before, and what they find is when you quench across the transition, actually they also saw it in this experiment. It's very interesting because so you have a certain knob, which is the strength of the quench, and actually there is a critical value of the quench beyond which the algebraic coherence change the measure. So it seems, that's what I believe, that there is a kind of dynamic phase transition, very much like the equilibrium one, but where the critical coherence will not be detected with the same. And typically, the algebraic coherence change the exponential when you start, when the balls there up to 10 times, and then the algebraic coherence there is most probably kind of dynamic transformation. But there's no complete so far as far as I know. Yes. Yes, probably. And what is not clear is whether if you cross the transition, the system will also converge. But there is also times here which matter. It's difficult problem.
More questions? All right, then let's thank Nicolas again. Next speaker, Pietro.